I'm David Rolnick, and this is Boris Hannon, who will be speaking for the second half of the talk. So we're going to be talking about the complexity of linear regions in deep nets. And I'd like to start out by giving some intuition for the kinds of problems that we're thinking about here. So basically, ever since people have noticed that deep learning works, people have also asked the question of why deeper networks are so successful as compared to shallower networks. And the way that this question has often been answered is through expressivity. Namely, deeper networks are better able than shallow networks to represent complex functions succinctly. You can represent a complex function using fewer parameters with a deeper network than with a shallower network. There are various notions of complexity that have been considered here. For example, topological invariance, path length, curvature, and actually what we're going to be considering here, which is the number of linear pieces in a piecewise linear function. However, there's perhaps an overarching point which should be made, and perhaps an overarching problem, which is that these notions of expressivity really rely upon very special networks. And in many cases, you have to set the weights and biases manually in order to obtain the kinds of complex functions that are needed to saturate these bands. We're interested in a different notion of expressivity here, which is potentially very different from theoretical expressivity. We'd like to ask, what is the typical complexity, or the practical expressivity of deeper networks as compared with shallower networks? One might ask this both for networks at initialization and also during the course of training. Are deeper networks still more expressive than shallower networks if you consider practical expressivity as opposed to this maximal theoretical expressivity, which might not actually be attained? One of the reasons why this is a reasonable question to ask is because of results like those of Ba and Caruana, who show that in many cases, shallow networks can actually be trained to do the same job as deep networks, if you first train a deep network and then train a shallow network to emulate it. Now, this suggests that perhaps deep networks are not actually taking advantage of their full expressivity, and they are in fact using something else, perhaps an inductive bias, that makes it easier for them to learn exactly the kinds of functions which we find interesting, whereas shallow networks find learning these functions harder, but are theoretically capable of expressing the same functions. So the particular notion of complexity that we're going to consider here is for piecewise linear functions, piecewise linear networks, of which the most common is definitely the ReLU, but actually all of our results will hold for any piecewise linear activation function, not just for ReLU. We'll state them for ReLU. So let's take a look at the notion of complexity that we're considering here. We're looking at linear regions here. So this is a plot of input space for a network that sees two-dimensional inputs. And what we've done is we've partitioned input space into a number of regions. Each of these colored regions represents a section of input space on which the network computes a single linear function. Since it is a ReLU network, in this case a randomly initialized ReLU network, input space can be partitioned into these linear pieces. Now, this is a very reasonable notion of complexity for such a network, because if you imagine some curvy function that you're trying to learn, the extent of the curvature is related to the number of linear pieces that you need. If you have a curvier function, you could imagine needing more linear pieces in order to interpolate it. Now, to get a better sense of how these things actually relate to the architecture of the network, consider what happens as you go through the network, seeing how the input space partition changes. Here we have two input nodes representing the two coordinates of the input space. And in the first hidden layer of the network, you see that each of these neurons is computing a partition, very simple partition, into two regions. Now, those two regions correspond to whether the neuron is on or off, whether its ReLU is zeroing out the input or whether it isn't. And each of these is a different partition into two regions for each of those neurons. Now, if you look at the second hidden layer, it's taking these partitions and it's computing what is essentially the common refinement of all of those partitions. And in addition, it's adding some divisions of those regions corresponding to whether these neurons are on or off. So essentially, at every layer, you take a look for each neuron at the refinement of the partitions above it, and then you also add a new split to several of these regions corresponding to that neuron being on or off. And that's how these regions are formed, and you end up with a very complex partition in the end. Now, formally, what we're looking at is a notion of linear regions that can be defined as the connected components of input space if you take away the boundaries of linear regions. And the boundaries of linear regions are exactly those points on which the gradient of the function with respect to the input is discontinuous. Since the gradient of any linear function is constant, on each linear region the gradient is constant, and so between linear regions there's a point of discontinuity. Oops. So the natural naive bounds which hold for the number of linear regions are there is at least one linear region. If you have just one linear region, then you are, in fact, a linear function. On the other side, you could imagine having 2 to the number of neurons linear regions. And that could be if every pattern of neurons being on or off corresponded to a single linear region. Are these bounds actually attainable? Can we have the lower bound? Can we have the upper bound? Well, the lower bound is very easy. We can easily have a linear network. The upper bound is almost attainable. We can get 2 to the depth of the network. It's possible to construct networks whereby you essentially double the number of regions at each layer of the network. And in the case of very deep and narrow architectures, that results in something very close to 2 to the number of neurons as the number of regions. So it's actually possible to get both of these bounds. But what happens in practice? What is the practical expressivity of networks? Are they closer to the theoretical maximum, or are they closer to the sort of stupid minimum? So what we find is that they're actually far closer to the stupid minimum. They're much lower in regions than one might expect. We find that along any 1D trajectory through input space, so you can imagine either a 1D input or a 1D subspace within your input, the number of regions that intersect that 1D curve is actually going to be linear in the number of neurons in the network. It's not going to be exponential. This holds for any reasonable distribution of weights and biases. In particular, we prove that this holds at initialization, but our assumptions strongly, our theorem strongly suggests that these assumptions will hold throughout training. And so we strongly suspect, theoretically, that the number of regions should be linear in the number of neurons throughout training. Something that is very interesting here is that this is actually independent of the architecture of the network. It's just dependent upon the number of neurons. So you could imagine a deep network and a shallow network with the same number of neurons having exactly the same complexity as defined by number of linear regions. Now, do these results actually hold in practice? These are theoretical results, and they rely upon various assumptions on the weights and biases, which are natural, but we need to verify them. And in fact, we find that this is true. If you train networks, they do have very few linear regions in practice. What we've done here is we've looked at networks trained on MNIST. We are here looking at a one-dimensional subspace within MNIST, taking various lines within the 784 dimensionals. So, can you hear me now? Is this better? We're looking at lines within the 784 dimensional space that is MNIST. And we are yes? I'm bad at mics, turns out. Can you hear me better now? Cool. So it turns out that we're looking at the number of regions over this particular 1D line through MNIST space, and we are normalizing by the number of neurons in the network. So there are various architectures, which we're looking at here. You can see that the top network, for example, is depth 4 and width 16. And what we see is that regardless of the architecture of the network, the number of regions is essentially the same as the number of neurons. At initialization, it starts out at basically exactly the same as the number of neurons. And then during training, it changes a little bit, but only by a very small constant. In particular, we never end up with an exponential blowup in the number of regions, which is what we would expect if the practical expressivity were in line with the theoretical expressivity. Let's zoom out a little bit, see what happens further on in training. Here we see 20 epochs of training on MNIST. The number of regions goes down a little bit and then rebounds, but it never deviates very far from our expected value, which is just the number of neurons in the network. Notice that this happens actually across architectures. The number of regions goes down and then rebounds. We see this in many different kinds of tasks, and we would like to draw a connection to an observed phenomenon, which is that networks will often learn to generalize before they learn to memorize. You can connect generalization and memorization to number of regions because a network that generalizes better is generally simpler, and a network that's simpler has fewer linear regions. So we would expect that networks which learn fewer linear regions are essentially learning better generalizing functions, whereas those which have an increased number of linear regions are better at memorizing. We see that networks are, in effect, learning a very simple function and then learning to adapt it to the exact vicissitudes in the data, which enables them to memorize better. We're not proving this, but we'd like to draw the connection between the observed behavior with memorization and generalization, and what we're seeing here quantified by the number of linear regions. I'd like to turn it over to Boris now, who's going to talk about intuitions and high-dimensional generalizations.
Thanks, David. When we first found that the number of linear regions in a deep ReLU network along a 1D slice of input space tends to grow like the number of neurons rather than something that depends strongly on the depth, we were a little bit surprised, so much so that we thought maybe the theorem is false. And so I want to present at least a brief intuition for why this ought to be true. To make the intuition precise, let me just introduce one piece of notation. So for each neuron that I'll call Z in the network, let me write its post-activation as follows. I'm going to write Z of X for the bias-free pre-activation of the neuron. Then the neuron is going to subtract its bias, B sub Z, and then you're going to apply the ReLU. That's my sign convention. So the basic idea for counting regions in one dimension is that the regions themselves are intervals, and rather than counting the number of intervals, I'm going to count the number of endpoints or boundaries of the regions. So a basic combinatorial kind of analysis will show you that if you have 1D regions, then the number of regions is equal to 1 plus the number of endpoints of the intervals. And so to count 1D regions, I'm going to rather count transitions. And as David mentioned, you're at the boundary of a linear region precisely when some neuron turns from on to off. And these region boundaries are therefore the inputs, where there's some region where in my notation the pre-activation Z of X is equal to the bias. So putting this all together, what do we find? We find that the total number of regions along a 1D slice of input space is 1 plus the sum over the neurons in the network of the number of inputs at which the neuron turns from on to off. So to show that the total number of regions is on average like O of the number of neurons, all I have to do is convince you that each neuron turns on and off O of 1 times. So how can this possibly be seen? Well, the function Z of X is a continuous piecewise linear function of its input, and solving Z of X is equal to BZ is like just asking how many times does it intersect the line, the constant line Y equals BZ. So you can only get many intersections if you have two simple conditions. So the gradient of the pre-activation has to be large so that it explores a large part of its output space, and the function itself has to oscillate so that it sees the same level of outputs many times. But precisely this condition that the gradient of the pre-activation is large is the kind of thing that means, for example, at initialization, your backpropagation will be ill-conditioned. So the very way we initialize networks shows that the typical gradients of neurons aren't too large, and therefore you only have not too many solutions to Z equals BZ. So that's the reason you have O of 1 solutions to this equation, and the number of regions grows roughly like O of number of neurons. That's our intuition. Okay, so in the last couple of minutes, let me briefly present a generalization of our result to higher input dimension. So rather than just counting the number of regions along a 1D slice, we're going to change our point of view and count the volume of the linear region boundaries. So rather than just looking at this picture, let me delete the colors, and these are just the boundaries of the regions. The kind of thing I'm interested in is counting the total perimeter of these black lines inside of this subset of input space. So our theorem goes like this. We first formally define B sub n to be the boundaries of the linear regions. These are the points of the discontinuity for the gradient of the network. And we observe that in input dimension 1, just like in the heuristic I just gave, the volume of the region boundaries is essentially the same as counting the number of regions. So you can view the volume of the region boundaries in higher dimensions as being a generalization of counting regions in 1D, and it's a different generalization than just counting the number of high-dimensional regions. So our main result is the following. It's very much like our original one. Even in higher dimensions, if you fix a subset S of input space, and you ask, what's the average volume of the region boundaries that intersect that subset? We get that on average, it looks like the number of neurons in the network times the volume of S. So for example, if S is just the unit cube, the number or the volume of the region boundaries is proportional to the number of neurons. And again, you see that it's depth independent, and in fact doesn't depend on the input dimension either. You don't win anything by having higher dimensional inputs. One of the reasons we thought this notion of complexity was really interesting is it allows you to probe the sensitivity of the network that you're actually training. Namely, you look at an input point to the network, and you ask, how far do you have to go from it to the boundary of its linear region? So a basic corollary of our theorem is the following. If you fix an input x, imagine some MNIST data point, the average distance from it to the boundary of its linear region is bounded below by 1 over the number of neurons in the network. And so the regions can't be too small. In fact, the typical size of the regions has a lower bound that's independent of the depth of the network. Okay, so because we only have a couple of minutes left, let me briefly flash a couple of experiments and then just give you the takeaways. So this is the same experiment David presented before, different fully connected ReLU nets trained on vectorized MNIST. The x-axis is again number of epochs, but now the y-axis is not the number of regions along a 1D line. It's rather the distance from a typical data point in MNIST to the boundary of its linear region times the number of neurons. This is the thing that the theorem predicts is bounded below by a constant. And what you see empirically is that it's bounded above by a constant as well. It stays approximately the same. And the dip that David mentioned turns into a bump. You know, the distance to the region boundary goes up because there are fewer regions and the regions are bigger. And so you can kind of slice this cake a different way. Rather than the x-axis being epochs, you can just make training accuracy be the x-axis. That's a more intrinsic way of measuring the time dimension. And we see, quite intriguingly for us, that it's approximately at the same test accuracy that the typical size of the regions is maximized across all these different networks. We're not sure why, and we're trying to investigate it. So to summarize, the main takeaway of this talk is that there seems to be a big gap between the practical and theoretical expressivity of deep networks. And more specifically, the practical expressivity for deep networks is very similar to that of shallow networks. And so expressivity is not quite as important as suggests as otherwise people would have thought. And so just to conclude, let me also say David and I have a recent preprint which counts the number of regions in any number of input dimensions. And we get a bound, which is that in given input dimension, the average number of regions, let's say in the unit cube in input space, is like the number of regions to the input dimension over input dimension factorial. So you see this notion of complexity depends on the input dimension, but again depends only on the number of neurons rather than the depth of the network. Thank you very much.
Hi. In the first half of your talk, you showed some diagram and the number of the linear region versus the neurons. And I have a question, is how do you actually measure the number of the region from a practical and meaningful size of the neural network?
Sure, it's a really good question. The question was about how we actually count the number of linear regions. So the way that we do that is progressively, like we show that picture of how the regions change as you go through the network. We add neurons one by one, and we see what the partition of input space is at each point, and then we keep track of the regions that exist at any point and add more and more neurons. The reason why we can do this in a reasonable amount of time is precisely because our theorem holds and there aren't that many regions.
This is supposed to be a very small network, right? If this is a very big network, the dimension is high and all these numbers just explode.
So we're looking at the number of regions along a 1D line. So the number of regions.
Over the 1D line.
Yes. Our results are holding for 1D subspaces of input space. So for example, within a 780 four-dimensional space, which is MNIST, we are looking at the number of regions along a line intersecting that 780 four-dimensional space.
1D line, right?
Yes.
But it's totally different story in the high dimension
well,
space.
Our future paper, our
I
paper,
know. The last one probably is,
yeah.
That's right. Make more sense.
So that's hard to count if the dimension is higher than, say, 2. Very good question.
I have 3 questions. Thank you for the great talk. My first question is, does this problem have any connection to the tropical geometry? My second question is, did you try any other piecewise linear activation functions and how the selection of the piecewise activation function influenced the phenomenon that you observe? And my third question is, how tight is the concentration around the expectation? Thank you.
Sure.
So about the tropical geometry connection, it might be there. We at some point discussed trying to find it, but we couldn't. We have nothing smart to say. About the concentration question, we don't have theoretical estimates for the variance, but you can see on the experiments that we ran several runs, and even if you plot the standard deviations, they're typically smaller than the mean, so you do get some concentration. And then the second question was?
Number of, if you have other piecewise linear activation functions, and exactly the same results hold, it's just you need to account for the number of breakpoints. You get a constant factor, which is the number of breakpoints in your function. So ReLU has just one.
Let's thank the speakers again.
So our models have a robustness problem. We're doing pretty well in IID settings where the train and test distributions are the same. But the moment you start evaluating models on even slightly different distributions of what you train on, performance drops. This is what robust algebra distribution generalization is trying to measure and solve. Just to give an example, you can take Inception V3, which gets 76% accuracy on ImageNet, and you evaluate the model with just moderate Gaussian noise, performance drops to 50%. And if you increase the noise level, you can drop it down to even 14%. We have benchmarks which are designed to measure this kind of robustness. One example is due to Dan Hendricks and Tom Dietrich on it's called the Common Corruption Benchmark. And it's more than just evaluating robustness to noise. There's also blurring, weather corruptions, and digital artifacts. And it's designed to measure the kind of distributional shift that models are going to face in the real world. Now, at the same time, there's a lot of work on the concept of adversarial examples. So in 2013, it was discovered that neural nets are sensitive to small perturbations of the input. It's been a very hot topic of study. There's well over 2,000 papers written on this topic. And it's often referred to as a surprising phenomenon. And when I first started to study adversarial examples 2 years ago, I also thought this was surprising. But I no longer think this is surprising, and I hope that in the 5 minutes that I have, I can convince you it's not surprising. So there's a lot of people asking the question of why do our models have adversarial examples? And I'm not actually going to answer that question because I don't know. But I want to answer a different question. What are adversarial examples? And my answer for what are adversarial examples is they're the nearest error. If you think about it, there has to be a nearest error, right? If you measure test error in the clean distribution or in a corrupted distribution like noise and blurring, you are telling yourself your model makes mistakes. And if you look for the nearest mistake adversarially, boom, there it is, you found it. And so this question, why do our models have adversarial examples, that's not really the question you're asking. The question you're asking is, why do our models have out of distribution test error? And that's the point we're trying to make, is that this phenomenon is not a distinct concept from more traditional notions of generalization and machine learning. So in this work, we make this connection between L2 perturbations and error rate and random noise. So for example, if you assume your decision boundary is linear, then a 1% error rate on random perturbations of norm 79, which is shown here, would imply an adversarial example at norm 0.5. And it just turns out that the decision boundary of neural nets closely resembles that to a linear model when you measure these two quantities. And so with this in mind, I just want to talk briefly about adversarial defenses. So I think there's a lot of great work on adversarial examples. I think neural net certification is great to study. The Magi lab has done a lot of really cool work with adversarial training. My issue is with this table in particular. Currently, mainstream robustness research in machine learning revolves around this table. And I think that's a problem, because this is just not a useful measure of robustness. You're evaluating the model on a very tiny fraction of the input space. It looks like you're doing a lot. There's 8 different attacks here, but it's this extremely limited robustness measure. And so I hope moving forward that we can think about robustness much more generally. The problem to solve here is the robustness to distributional shift problem. And we have benchmarks that are designed to measure this. And maybe we can get models robust to L infinity perturbations, but that's not going to be very useful because there's still going to be a nearest error in other metrics if you haven't solved the distributional robustness problem. And so just to conclude, it should not be surprising that models have a nearest error, and I hope moving forward we can think about robustness a little bit differently. Thanks.
My name is Eduard Yalon, and this is a joint work with Eugene Bejovsky and Michael Eichenberg. So the idea of this work is to show that we can numerically obtain some competitive neural network via Layerwise tuning procedure using shallow networks. So, as you might know, the initial and the final layer of CNN have well more structures than the intermediary layers. And so in our work, what you see on the left is that there is a joint, the typical joint loss that is used versus on the right, layer-wise join that we do study here. So our goal, in fact, is to remove the joint end-to-end constraint during training. So in other words, we wonder if we can explicitly specify the objective of each individual layers. So to go beyond the black box optimization of deep neural networks. So the motivation of work is first because shallow networks have way more literature, like in terms of guarantees or optimization. And also, I mean, since the inner organization of the layers are not well understood. So also most of the studies only limit to 3 layers at maximum. So we wonder if like using shallow network can help to reveal some structure in the organization of deep neural networks. And so also we wonder if theory in fact can work in practice. So first we start with this empirical observation that typical neural network has a tendency to contract and to separate the different classes for an image classification problem. And in fact, if you use a linearized VM at each individual layers, you see that the accuracy of your linearized VM is going to progressively improve. And so we wonder if reciprocally, we can use this criterion of linear separability to train a neural network. So to do so, we simply use a greedy layer per layer procedure that does consist in, in first, what you see here is an initial layer that is cascaded with an auxiliary classifier. We train it until convergence, and when it has converged, we freeze it. Then again, we cascade a second layer, we train it until convergence, and again, we're gonna freeze it, and we continue this procedure iteratively. And so it's a very simple idea that was in the literature for a while. However, it had never been shown to scale on a large-scale datasets such as ImageNet. So here, K does correspond to the number of point-wise nonlinearity that is used at the training. So first we consider the case K equal 1. So here that means that we train each layer of our neural network via one hidden layer of neural networks. And so in other words, it means that the explicit goal of the layer that is trained is to linearly separate the different classes. And so what we show is that we are competitive with an AlexNet on ImageNet. So then we did try some deeper CNN. So we use K larger than 1, and so we observe that there is a significant improvement. And so it seems to indicate that depth is a key ingredient for training those greedy networks. Also, we did some layer-wise studies, and so we show that numerically there is an improvement, a progressive improvement layer per layer until a plateau. And so in our paper, we also conduct more experiments to study those phenomena. So in conclusion, we demonstrate that greedy learning can scale to ImageNet. Intermediary layer objectives are better specified through progressive linear separability. And also, I mean, if we could build a good one hidden layer procedure to train the neural network, then our work tends to show that we could train a deeper CNN. And finally, I would like to mention an ongoing work about decoupling layers for parallel optimization. Thank you.
My name is Sufyan from University of Oxford. I want to talk today about the impact of activation function on deep neural networks from an information propagation point of view. So first, let us just consider a feed-forward neural network initialized with the Gaussian distribution. So as the number of neurons per layer goes to infinity, so in the limit of large width, we have this concentration phenomenon using the central limit theorem. And so the value of the neurons will converge, will become Gaussian. And using this for all the layers, we can conclude that when we have a large width neural network, we will finish with a Gaussian process. This was first introduced by Neil, and then generalized recently. Okay, using this limit of infinite width, we can study information propagation, such as variance propagation, correlation propagation, to see how this information propagates through the layers. Okay, so in 2017, it was established that there is, for example, for the correlation, there is a depth scale, which means that the correlation between two inputs will converge to some constant value exponentially, but we can solve that problem using what we call the edge of chaos, which is just an equation verified by the parameters of the initialization sigma b and sigma w. So just to remember, sigma b and sigma w are the variances of the initializations. Okay. So this equation called the edge of chaos, it separates two states. The first state is the ordered phase, to which the correlation converges exponentially to 1. So the constant c here is 1. In this case, we will have, for two inputs, the output will be the same because the values are Gaussian, and we have the correlation equals to 1, so the outputs are equal. And we have the other phase, which is the chaotic phase. In this case, we will have, for two very similar inputs, the outputs are very different. So we can see this in the ordered phase for a neural network with the depth 20 and width 300. We have a constant output. This is in the chaotic phase, so it's very discontinuous. So the edge of chaos, as we said, is just an equation verified by sigma w and sigma b. And we can show that this equation is linked to an infinite depth scale and also a sub-exponential convergence rate for the correlation, which means that we don't lose the information exponentially, but we lose it at a sub-exponential rate. For ReLU, this initialization, this edge of chaos coincides with the recommendation of he and al. Okay, we can also show that an interesting fact about this edge of chaos initialization. Actually, for a ReLU network, when we initialize with at the edge of chaos, it acts as if it was a residual, a simple residual neural network, and we have this the convergence of the correlation is in 1 over L squared. Also, we studied the impact of smoothness. So if we choose a smooth activation function for class A, from this class A, which includes ILU and tangent hyperbolic and swish, for example, we can show that we can improve the rate at which we lose the information to 1 over L. So compared to ReLU, it is better than ReLU, okay? Yeah, we just plot some experiments here, which shows that this 1 over L convergence rate. And here we show some just experiments. For example, here we do the training with the edge with an initialization on the edge of chaos, and we do one with the batch norm. Sorry. This is the last slide. Here we show we only show the impact of the smoothness of the activation function. As you can see, ILU and tangent hyperbolic are better than ReLU. Thank you.
So I'm Ziv. I'll be talking about information flows in deep neural networks. And this is joint work with my IBM collaborators, Iwat, Christian, Igor, Naman, Brian, and Yuri from MIT. Okay. Yeah, so getting into things, while deep networks enjoy some unprecedented practical success and many important tasks, I think it's also fair to say that theory-wise, we still have quite a long way to go, mainly in a sense in our macroscopic understanding of how those systems operate, with many important questions about this topic that remain unanswered up until now. So things like what drives the evolution of internal representations throughout the epochs of training of the system, and I mean, in terms of whether there is some grand principle according to which this evolution occurs, right? And even on top of that, we don't fully understand what are the properties of internal representations once the network has finished training, or how these representations are used in the information processing procedure performed by the network. And unfortunately, the list goes on and on. And of course, there have been many attempts to address some of these issues, and more generally, just the question of why have deep learning been so effective in practice. And this is a very partial, I would say, literature review. But today I would like to focus on the information theoretic approach, and in particular on the information bottleneck theory by Naftali Tishby, because while this theory tells a very beautiful and intuitive story to explain deep learning, it also at the same time relies mostly on heuristic arguments that really strive for some mathematical scrutinizing. And such a rigorous mathematical analysis is exactly sort of the core objective of this project, which I would like to leverage today in order to mathematically and even geometrically explain the so-called compression phase of deep neural network training. Okay? So to set things up, I want to consider a vanilla feed-forward deep neural network for classifying a feature X with respect to its label Y. And such networks, when we fix their parameters, they just define a deterministic mapping from input to output, which is specified by the relation that each layer is given as some deterministic function of the previous one. And letting this PXY be our joint feature label distribution, with such a deterministic network model at hand, this PXY will induce a joint probability law over the entire system. And it is with this law in the background that the information bottleneck theory proposes to study deep neural network training or learning dynamics through the so-called information plane. And this would be just a two-dimensional plane with an axis corresponding to each of these two mutual information terms, where the first one is the mutual information between the input feature and the vector of internal representations specified by a given hidden layer TL, as well as the corresponding mutual information between the true label and the internal representation vector. And with this in mind, this is the claim from the information bottleneck theory on which we'll be focusing, that asserts that whenever you train such a deterministic feed-forward DNN with stochastic gradient descent, the internal representations indeed evolve according to a common grand principle, and with respect to this principle, training comprises of two inherent phases. The first is a short fitting phase, which is described in the information plane basically by both mutual information terms rising, which is when the network learns to fit the data. And when this is done, the system enters the phase of compression, which takes up the vast majority of training epochs and is dedicated to slowly reducing this IXT mutual information with the input, while hopefully staying as informative as possible about the label we're trying to learn. And this is over here a typical illustration of those two phases in the information plane, where each trajectory corresponds to a different hidden layer of an underlying network trained to perform a certain classification task, each showing the evolution of our mutual information pairs across epochs of training of the system. And I think we can easily see the two phases I've just mentioned, with this being the short fitting phase, followed by this leftwards kind of shift or movement, which is this slow phase of compression. Okay? Now, the information bottleneck theory intuitively explains this compression phase as the network trying to shed or forget information about X, which is irrelevant for the classification task we're trained for. But we honestly wanted to understand the mathematics and perhaps even the geometry in the background here, so we sort of decided to dig a bit deeper into that. And once you do, you quickly realize that there's a fundamental theoretical flaw behind this claim, because one can prove that for any fixed deterministic DNN with strictly monotone nonlinearities, such as, by the way, the network for which the compression plot from the previous slide was generated, well, in any such network, the mutual information of interest IXT is provably independent of the parameters of the system. So while these parameters evolve during training, mutual information is ignorant to that, and in particular cannot compress. Now, to be a bit more specific, IXT is almost surely either infinite or constant for continuous or discrete X respectively. And to see why this happens, for instance, for discrete X, well, the reason is, roughly speaking, the following. So imagine this is our feature space, and take X to be uniformly distributed. Oops, sorry. Yes, take X to be uniformly distributed over the 3,000 samples we have from this spiral data set. Now, while the deep neural network changes the geometry of this input signal as it maps it to the internal representation space, maybe something that looks roughly like this, Up to a zero-measure set of weight matrices, these mappings turn out to be injective on finite sets. And when you combine this injectivity with the invariance of mutual information to invertible transformations, you get exactly this degeneracy property that we're currently speaking of. Okay? And the reason why past works essentially miss this fact, and despite it empirically observed compression, is really rooted in their misestimation of mutual information, because you see what they do is compute a certain binning-based proxy of this mutual information quantity by quantizing outputs of neurons as part of the computation process. And the problem with this is that, first of all, it gives an approximation that differs from the truth for any relevant bin size. But the even bigger issue is that it further turns out that this approximation is very, very sensitive to its user-defined parameter, which is this size of the bin. And this is what you get when you repeat the binned IXT mutual information computation versus epochs of training from the previous slide, but for 4 different values of the size of the bin. And then I think it does look pretty arbitrary. And you can also see the convergence to a constant as the bin size shrinks to 0. And the bottom line here is, because they quantize those neuron values as part of the computation process, but nothing is really quantized during the training process of the actual network, we end up getting this mismatch between the true mutual information, the theoretical quantity over our system model, and the quantity that we end up plotting, which further means that all those fluctuations we're seeing in those plots are an artifact of what's at the end of the day are just estimation errors. Okay? And because we wanted to rigorously study this IXT mutual information and sort of isolate the phenomena in the background, what we basically decided to do is to move to an auxiliary framework, which is, first of all, a good approximation of the deterministic system we started from, but such that over this auxiliary framework, information measures are meaningful system-dependent quantities that are sort of prone to a rigorous analysis. And this auxiliary framework is what we call a noisy deep neural network, a very simple modification of the original deterministic system that simply injects a small amount of IID Gaussian noise to the outputs of each and every one of the network's neurons. And it's important to understand that the noise here is intrinsic to the system. The network is trained with noise, it evaluates with noise, and therefore the mapping it defines from the input to the internal representation space is no longer this injective deterministic function, but rather it becomes a stochastic parameterized channel whose parameters are the weights and the biases of the network, and consequently the true mutual information over the system model starts to be a function of those parameters as well, just as we wanted. Okay? So great, we have our auxiliary framework. Mutual information is now meaningful. The question therefore becomes, how do you actually track or estimate this quantity? And unfortunately, I won't have time to get into this whole separate mutual information estimation question, so I'll pretty much skip this slide, but I do want to say 2 main things. The first of which is that we prove that this problem is inherently difficult in the sense that any good estimator of this mutual information within a small additive gap must have a sample complexity over here, which is exponential in the dimension of the problem, when dimension corresponds to the width of the hidden layer of interest, which is a tough spot because this sort of immediately limits us to small-scale experiments if anything is to be estimated correctly or accurately. But then on top of that, we develop an estimator for which we prove its performance scales optimally both with the number of samples n and the dimension of the problem d, which now at least gives us a tool in those small-scale experiments to accurately estimate mutual information, generate some plots, and try to test for compression. Okay? But as a maybe one last step before I show you any of these plots, what I would like to do is to try to use this very simple example to sort of develop a feeling of what we should be expecting to see there. And the way it works is that I want to use this single noisy hyperbolic tangent neuron to classify an input that takes only 4 possible values, plus minus 1 and plus minus 3, such that our 3 leftmost values are together our first class labeled -1 colored blue, while the remaining input element 3 is a second separate class labeled 1 colored green. Now, looking at the output of the stanch unit, if this is how the system is initialized, then what we essentially want to do for classification is, first of all, center this hyperbolic tangent curve in between our 2 classes and then sort of sharpen its transition, generating an output that looks like this, under which classification performance is perfect, because we can see that these three blue inputs over here, whose representations at first were sort of all scattered all over this y-axis, are now tightly clustered together under a correct label of -1. And the same goes for the green input, which is mapped to its own correct label of 1 and separated from the rest, which, yes, was a big shock. Yeah, so, of course, this is all very simple, but the interesting part is how this connects to the mutual information between X and T that we're trying to figure out. And to answer this, let me rewrite this mutual information as the mutual information between the output of the tanh unit and its noisy version. And I'm again using the invariance of mutual information, two invertible transformations here. And looking at this right-hand side, well, this is actually a quantity we have a very good understanding of, because this is nothing but the aggregate number of bits, or nats, depending on our units, that are reliably transmittable over an additive wide Gaussian noise channel with noise variable z, using an input that is uniformly drawn from a constellation that is generated by the output of this tanh unit. And like we saw in the example, while upon initialization, those constellations might contain 4 distinguishable symbols at the output of the channel, as we train the neuron, the constellation converges to a binary constellation that contains only the 2 correct labels, plus and -1, thus reducing the number of transmittable symbols from 4 to 2, and consequently causing a drop in mutual information. And this is exactly what we see when we train the neuron, and here I'm showing a heat map of the probability density function of this Gaussian mixture variable t versus epochs. And again, we can see 4 perfectly distinguishable Gaussians at the output of the channel at the beginning. But as training goes on, we get this progressive clustering or merging of representations of inputs that belong to the same class. And when you compare this to the trajectory of mutual information versus epochs of training, we can see that at the exact epochs where these merges occur is when the mutual information drops from representing 4 transmittable symbols to 3, and then finally to 2, once the network has converged. And I mean, this is compression, right? Just drop of mutual information. So at least in this small example, we're able to conclude that what drives compression, its source, is nothing but this progressive clustering of equilabeled inputs. And the really nice thing about this observation for me is just how well it generalizes to larger experiments. So let me show you that next. And what I want to consider here is basically a noisy version of the original DNN studied by Tishby, where he first observed compression that performs a binary classification of a certain synthetic data set using this fully connected hyperbolic tangent architecture. And the plot I want to show you is this, which is kind of busy. So let me break it down. Here in the middle, these would be the estimated curves of mutual information for the different hidden layers versus epochs of training. Below, training and test loss, and there's sort of a whole separate discussion to be held here. But really, what I would like to point your attention to here is those 4 scatter plots on top that show the internal representations of the entire empirical input data set when it is propagated all the way up this network to this last 3-dimensional hidden layer of the system. And what I would like us to note is really what I find is the remarkable correspondence between the trends of mutual information for this last hidden layer shown in teal, its rises and falls, and just how spread out or clustered the internal representations at the corresponding epochs are. Okay, and what I'm only showing you the single example here, we have verified this observation in multiple additional experiments, all of which leading to the same conclusion that compression of IXT mutual information over noisy networks is driven by clustering of representations, and you're welcome to visit us at the poster to see some more of these experiments. But the last thing I want to do in this talk is to sort of try and build on this realization to circle back to deterministic systems and try to figure out what we were seeing there as well. Because when we're back in the deterministic world, mutual information, again, a vacuous quantity, no longer, if you will, this sort of device for measuring clustering, but knowing what to look for, we've just re-examined this binned mutual information that was measured over deterministic networks in past works from the clustering perspective. And because the network is deterministic, this mutual information reduces simply to this discrete entropy of the binned internal representation. And after some further calculations, one can convince himself that this discrete entropy is nothing but a very, very natural way to measure this exact same old clustering inside the internal representation spaces, essentially because discrete entropy is maximized by uniform distribution over those bins. And this is beautifully seen when you compare trajectories of this binned entropy to those of the true mutual information over a noisy network. And yeah, which we already sort of know that tracks clustering, and just observe how correlated they are with one another, with mutual information shown on top and bent entropy here at the bottom. And based on such observations, we were able to conclude that this is in fact exactly what those past observations of compression in deterministic systems were showing, not the theoretically impossible compression of mutual information, but rather this, if you will, profile of the amount of clustering inside the internal representation spaces across the epochs of training of those deterministic deep learning systems. And let me, just as a sort of side remark, as a byproduct of this clustering perspective, we were also able to, in fact, refute this claim by the information bottleneck theory that more compression, or in our language, tighter clusters, always implies better generalization, essentially by providing counterexamples. And again, visit us at the posters to see details about that. But yeah, with this, let me quickly summarize. We've re-examined this information bottleneck theory from the perspective of the compression phase of training, because it is theoretically impossible, but then it was empirically observed through this lens of bent mutual information in past works. And to figure out what was going on, we moved to this noisy DNN framework of ours, which enables rigorously study information measures. And by developing this optimal mutual information estimator, we've been able to isolate clustering of representations as the source of compression of IXT over noisy networks, and use this realization to clarify that past observations of compression in deterministic systems were measuring the same old clustering with, like I said, the byproduct result that compression and clustering and generalization are not necessarily connected simply as one just implying the other. And with that, guys, I'll stop. Thank you for your attention. Be happy to take any questions. Thanks.
I was curious about the last result you mentioned about the relationship between compression and generalization. It's cool to know that they're not straightforwardly related, but can you talk a little bit about what is the relationship?
So yeah, finding out what is the exact relationship would be awesome, and establishing some mathematical result that connects the two. This is something that we're currently looking at. What I can tell you at the moment is that it's a good thing I didn't delete the backup slides. So this is the plot I showed you, right, where you just sort of vanilla train this network with SGD or Atom, and you get compression of mutual information, tight clusters forming inside internal representation spaces, and mad overfitting, as you can see by this blue train versus red test curve. Then a second sort of trial of the same exact experiment, you add basically Perceval regularization to your loss function that sort of suppresses the ability of the network to form those tight clusters inside the internal representation spaces. You train this network from the get-go. You do not get any tight clusters forming inside the internal representation spaces. Compression is completely gone. Mutual information, in fact, grows, and overfitting is gone as well, and the network generalizes much better. So this, for us, suggests that, here is an example of a network that generalizes much better when nothing is clustered inside internal representation spaces or compressed in terms of IXT mutual information. So all I'm saying, there's a much more delicate relation there, and it should be further explored. Yes.
Hey, Zev, great talk. Can you perhaps comment on how different activations affect the information plane dynamics? And does maybe adding regularization terms to the neural network alter them?
Okay, so you're asking how different nonlinearities affect the dynamics. Yeah, so okay, it's a good question. So let me say it like this. So long that the network has the ability to cluster representations, which for maybe tangent sigmoid would be basically pushing things to the vertical asymptotic regions of the nonlinear functions. For ReLU, maybe just shoving stuff into the negative half of the real line. So long that the network has an ability to cluster representations, it at least based on our empirical observations, it does so, and when it happens, mutual information undergoes this phase of compression. And there was this, I think, past work, right, that sort of argued that if you can doubly saturate your nonlinearities, you will compress, otherwise you might not. This is not what we're seeing. Anytime you can cluster, you will observe compression. As far as regularization, if you sort of actively suppress the network's ability to form tight clusters, maybe by restricting matrices to be orthonormal or something like this, so it can no longer just grow all the weights at once. So yeah, clustering will disappear, compression will disappear as well. They're sort of go hand in hand.
Let's thank the speaker again.
Thank you, guys.
This work is about analyzing noise in stochastic gradient descent. So it is widely known that SGD tends to generalize better than gradient descent in deep neural networks. So this is mainly due to the noise introduced by the stochastic gradient descent. So previous work mainly studies the noise magnitude of the stochastic gradient descent, like the learning rate and the batch size. So in this work, we move a little further to study the anisotropic structure of the SGD noise covariance and how it will influence the escaping from local minima and its regularization effect. So now we consider about the loss function. The loss function L, big L here, is kind of an n-term included different data points you want to train with, right? So we consider some variants of the stochastic gradient descent. The first one is the gradient Langevin dynamics. Basically, is a full gradient plus some isotropic noise. So variance is the sigma t square here, right? So another one is the standard SGD we use, basically sampling with the mini batches, but the noise structure is a little complicated. It's a covariance of the gradient, stochastic gradient, right? So this motivate us to study a more generalized form of the gradient descent dynamics with unbiased noise, but the covariance structure is quite different. So we want to study the different covariance structure, how it will affect the learning dynamics. So we can approximate it with the stochastic differential equation with this, right? So we now analyze the effects of the noise covariance segment here, right? So we define and derive the escaping efficiency as the expected deviation of the loss function from the original minima L theta 0 here. So with some assumptions, we can approximate this escaping efficiency with the t times the trace of the h times the sigma here. The h is the loss, is the curvature of the loss function. The sigma is the noise. So this trace here serves as a kind of a very important indicator to measure the escaping behavior of the different noise, right? So there are three factors affecting the escaping behavior. The first one is the noise magnitude, right? To eliminate this effect, we just fix it as a constant of this trace. And the other factors like the structure of the curvature and the noise covariance in your learning dynamics. So this is what we care about. So we provide a proposition that if the following two conditions hold, the escaping efficiency of the anisotropic noise will be much faster than the isotropic variance. The first condition is the curvature is a condition, and the second one is the sigma, the noise covariance aligned with H. So later we analyzed the noise of SGD in deep neural networks. We verify theoretically that the two conditions are satisfied in neural networks and SGD for optimized neural networks. So yes, so we then conduct various experiments in 2D synthetic and the real neural network training to see that the conditions of SGD can be satisfied, and the SGD noise can help us to find to escape the sharp minima, to find a flat minima, and can generalize better. So the final conclusion is that the noise covariance structure of SGD is quite important for generalization. So if for more information welcome to our poster tonight, 97. Thank you.
So I'm Antoine Labati. I will present my work on the characterization of deep neural networks. So the starting point for this work is that there is still no mature and satisfying theory that's able to validate the full choice of hyperparameters which lead to state-of-the-art deep neural networks. And this theoretical gap has attracted much research, and many research works have focused on networks at initialization. And there are two reasons for studying networks at initialization. So first, these networks can be proxy for the full hypothesis space. And second, the initialization in itself is important because it's the starting point of the optimization, and thus it should be well behaved. So in this context, we bring two contributions. We introduce a novel and unifying methodology for this characterization of neural networks at initialization. And second, we use this methodology to characterize the most common deep neural networks. So our first contribution, the methodology, and our first methodological brick is to consider the propagation. And we consider the propagation of two tensors, the standard neural network signal and an additive noise which corrupts this signal. And then this propagation is considered in three contexts: in the context of vanilla nets with only convolution and ReLU layers, in the context of batch normalized feed-forward nets with the further inclusion of batch norm layers, and in the context of batch normalized res nets with the further inclusion of skip connections. The second methodological brick, we introduce the randomness which comes from the input data. We first define two quantities, so the effective rank of the signal measures the number of dimensions in which the signal effectively lives, and we define the normalized sensitivity, which measures to which extent the noise is amplified with respect to the signal. And using these quantities, we are able to define two pathologies. The first pathology is characterized by the effective rank converging to 1, indicating that the signal gets concentrated onto a single line. And the second pathology is characterized by the explosion of the normalized sensitivity, indicating that the signal gets drowned in the noise. As last methodological brick, we introduce the randomness which comes from the model parameters. And the key is simply to treat the quantities we define, the effective rank and the normalized sensitivity, as random variables which depend on these model parameters. So now we arrive at the second contribution. We apply this whole methodology to our three contexts. And what we obtain, both theoretically and experimentally, is that vanilla nets and batch normalized feed-forward nets are pathological. So vanilla nets suffer from the pathology of one-dimensional signal, and batch normalized feed-forward nets suffer from the pathology of exploding sensitivity. On the other hand, batch normalized res nets are well behaved with no collapse of the effective rank and no explosion of the normalized sensitivity. So the takeaway is that there are two opposing forces acting in the background. So there is the additivity of the convolutions with respect to the width dimension. This additivity repels from pathologies. And the second force is the multiplicativity of the layer composition with respect to the depth. And this multiplicativity attracts to pathology. Because they are subject both to the additivity and multiplicativity, feed-forward networks are pathological at high depths. On the other hand, batch normalized res nets are only subject to additivity and not to multiplicativity, so they remain well behaved at all depths. So if you want more information, you're very welcome at the poster 98 this evening. Thank you very much.
So as you know, that encoder-decoder CNN such as UNet has been widely used for various inverse problems, like a denoising problem, or like a super resolution problem, or image impending problem, and etc. It's actually it's quite interesting that some network architecture works for various inverse problems. Why this is the case? In order to address this problem, let's revisit the classical method for inverse problem. Usually the classical method starts with defining the signal representation. For example, X is a unknown signal, then this is represented as a linear summation of the synthesis basis, and also the expansion coefficient is defined by the analysis basis. Now, based on this representation, classical method try to find the optimal representation by solving optimization problem with respect to the data fidelity term. For example, in the compressed sensing problem, they try to find the sparse representation as the optimal representation. Now, this kind of approach looks very different from the neural network approaches. Then, is there any kind of link between the two? The take-home message of this paper is, in fact, there is a very close relationship. In fact, actually, the neural network, encoder-decoder neural network, can be represented as a basis representation. For example, the analysis basis is coming from the encoder part of the neural network, and synthesis basis is coming from the decoder part of the neural network. We can actually have the explicit representation of the basis. For example, in the linear encoder-decoder CNN without Layerwise, we can show that the analysis basis is coming from the cascade multiplication of the encoder layer matrix, which is actually calculated as a convolution between the pooling matrix and the Lund filters. Similarly, the decoder part of the synthesis basis is coming from the cascade multiplication of the decoder matrix, which is also coming from the convolution between the unpooling matrix with the decoder filters. Then what's the role of the skip connection? It turns out that skip connection gives a more redundant representation of the basis, in fact, and make this representation more expressive. And furthermore, we can show that if actually the pooling layer and also filter layer satisfy so-called frame condition, these kinds of encoder-decoder neural network satisfy the perfect construction conditions similar to the wavelet basis. However, this kind of linear network is not interesting. We are actually interested in the neural network with the Layerwise layers, for example. It turns out the basis representation does not change too much. Only difference is there is a diagonal matrix in between with the 0, 1 values, and which is determined by the Layerwise activation patterns. In fact, what happens is in the Layerwise activation pattern is determined by the linear convolution. That means the input space is partitioned by the hyperplane. And after the neural network is trained for the given input, then neural network automatically assigns each partition and corresponding to the linear basis representations. And furthermore, this kind of theoretical expressivity of this neural network, we can actually see that the number of representation increasing with the channel, exponentially with the channels, and increasing with the network depths, as well as it's increasing exponentially with the skipped connections as well. Furthermore, this kind of representation also gives a hint how to actually calculate the Lipschitz constant for the neural network. For example, in this kind of cases, we can see that the global Lipschitz constant is determined by the local Lipschitz constant for each partitions, and that actually, based on that, you can actually compute the global Lipschitz constant. Furthermore, we can find a way to relax the optimization landscape. For example, in the prior work, they also show that if the feature layer has a fully connected layer and with the independent features, and then decoder path is a full-length conditions, then the neural network landscape is benign. We can further relax the condition and show that if there is a skip path with the independent features and the corresponding decoder path is a full-length condition, we can show that this optimization landscape is also benign. In conclusion, in deep learning, encoder-decoder network is a novel signal representation using combinatorial framelit representations. And in fact, the Layerwise generates multiple linear representation by partitioning the input space. For more details, please come to our poster number 99. Thank you.
What I want to talk to you today about is work we've done in analyzing traditional and heavy-tailed self-regularization in neural network models. So the motivations here for us were trying to get a broader understanding of why deep learning works. From a theoretical perspective, there are a number of open questions. For example, deep learning appears to be a non-convex optimization problem, and yet in practice it appears to be convex. There are many broad, open questions about what is regularization? What does regularization even mean in deep learning? It appears to be very different from what we understand in other contexts. For me, I studied the theoretical physics and statistical mechanics of neural networks back in the 90s. And we didn't really use VC theory. We did other things. So I think maybe what I'm doing is probably a little different from what a lot of people do, but there's some questions. Should we use VC theory? Should we use statistical mechanics? Should we use something else? But because I do applied work, we're also very practical things. Like, can we ask practical questions about deep networks? So what we're going to do, what we have done here, once you just consider the energy landscape of a neural network, and we are going to, this is just the general optimization function, the energy function. We minimize the loss. Usually there's some form of regularization. The regularization is usually thought to depend on the weight matrix. So what we're going to do is we're going to turn off all the regularization, and we're going to look at the weight matrix, and we're going to study its empirical properties. I'm a physicist. My approach to theory is I do physical experiments, I look at the results, and then I try to build a theory that describes the experiments. So we've looked at hundreds of pre-trained neural networks, thousands of weight matrices to try to understand what's going on and build a theory around it. The theory we're going to use, basically we're going to use something like random matrix theory. If you look at the spectral density, that is the eigenvalues of a weight matrix, and you sort of look at a small model and you look at what it's doing, it starts off at epoch 0, it sort of looks like a random matrix, and as the epochs progress, you see this little shelf pull out, and this is, and this little shelf toward the right, around the value 3 is typically where you think of the information being concentrated. And when you look at small models, they sort of look like this. And this is understood. This is called a spike covariance model, really understood in terms of the context of random matrix theory. And I think most people may be familiar with random matrix theory in the form of Marchenko-Pasteur theory. And I just sort of put this here. But in fact, in physics, there's not just Marchenko-Pasteur describes Gaussian random matrices, but in fact there's a whole series of different classes of universality classes of random matrix theory which are heavy-tailed. There's Gaussian random matrix theory, spiked covariance models, and various heavy-tailed universality classes which have been identified and characterized in the theoretical physics literature and also in computational finance. I was a quant at BlackRock, and we use these techniques to characterize the covariance matrix when doing portfolio theory, so that's how I'm familiar with them. So what we do is we're going to take our theory is basically heavy-tailed random matrix theories that we're using as the basis of theory. And each of these universality classes we can actually observe during the training of a neural network. So in this case, we just take a simple model, small model, and we systematically decrease the batch size. And as we decrease the batch size, you see that our models you go from something which is fairly random-like, bleeding out, to where it eventually becomes heavy-tailed. And we sort of call this the 5 phases of learning, 5 phases of training, which phenomenologically correspond to the universality classes of random matrix theory. But what you would find is if you look at pre-trained networks, older models, like I showed you before, like LNet-5, sort of look like traditional regularization. There's a random matrix part, which is described in red. There are some spikes. There's a cutoff. This looks like 10 cutoff regularization. Every other model we have looked at looks like a heavy-tailed system. If you go and you just download a pre-trained model, compute the eigenvalues, you'll find they fit to a power law distribution. And in physics, when we see power laws, we think strongly correlated systems. So what we have done is characterized all of these pre-trained models in terms of looking at strongly correlated systems. So you can come to our poster. We have a tool called Weight Watcher, pip install Weight Watcher. It will analyze the weight matrices for you, and you can do this yourself. Come to our poster. We're also giving a talk. There'll be a talk and a poster on Friday during the theoretical physics workshop. Thank you.